All right, good afternoon. Welcome back. Hope we had a great weekend. Today is September 19th. It is our 6th class. We are covering two topics today, models and applications, which has quite a bit of overlap to what we did last class, and then systems of linear equations. So we're going to be solving similar problems to the ones that we did on Friday, just using a different technique. On Friday, for the most part, we tried to keep everything in terms of one single variable, just x or something like that. Today, we'll have x's and y's, and then some techniques that I think you've seen in previous math classes about how to solve two equations with x's and y's in them. All right, a couple of logistical things. Number one, quiz number one is due on Wednesday, which is troubling for you because you don't have quiz number one in your possession. So I'm going to hand that out today. It is a take-home quiz. The instructions at the top are very explicit, but you'll read them later on. But it says you may use any resource at all while you take this quiz except for the help of another person. Anything you want, but not people. That means not each other. That means not me. That means not somebody in the math studio. It means not somebody in the peer tutoring. I've listed a few of the allowable resources up here, but there are more resources you can use than this. But some things you might find helpful to have nearby when you're taking this quiz are the filled in class packet. You're also welcome to download my version from Moodle, right? All the stuff I've written. You can use your textbook, which is on Moodle. You have a full version of your textbook and ebook. You can look at all of your old homeworks, on My Math Lab and possibly in your notebook where you've written down all of your work. You can use any book that you want. You can use any website that you want. It would be cheating to go to some website and ask a question for people to respond. That's equivalent to using another person. Yes? Right. Okay. You can use your calculator. You can use lots of other things. Don't go crazy with all the resources. Honestly, the most efficient use of your time as you take this quiz, and there's no time limit on the quiz, which is good, but it's also kind of dangerous if you're obsessive about like, I'm going to look at 17 resources before I write the answer to this first question. My recommendation is that you just try to take the quiz on your own and like have these resources nearby. And if you get stumped or you're not sure that you have the right technique, then, start to just use like a little bit of the resources, like the packet might be enough. But if you find yourself using all of these things, you're going to be taking, like 10 hours for a 20-minute quiz. There's no time limit, but just to be efficient and maybe and also get like a realistic sense of how much you have in your brains right now versus how much I'm expecting you to have. Do as much as you can just on your own, just like as if it were in class, right? But know that you've got these things as backups. Pete.
So this class multiplied for 50% section.
I don't know. I don't know that it's like an equal percentage of from the material.
Well, what I really was
I don't know. You'll see it. You'll see it in a couple minutes. I'm gonna give it to you, and then you're just gonna put it away and you'll look at it. So, but I'll just hold it up. Let's see. The first one looks like it's a word problem, and then let's see. It's 3 questions there, and no word problems there, and no word problems there. Some true false, just like we've been doing in the activities, and then the one big word problem is here on the back. So that's the entirety of the quiz. 2 pages, front and back. Okay, I said 20 minutes. I just made that up. Looking at it just very quickly here, no more than an hour, I would say. 20 minutes is probably an underestimate of how long it would take. But again, no time limit, but do as much as you can without the resources first. Okay, the other thing is that you are going to right now put the project. The project was supposed to be due Friday, but I pushed it back to today. You're gonna put those completed projects in the green folders right there on your table. So do that now if you haven't done so. If you don't yet have the project completed, you are going to want to complete it as soon as possible. I assume that my syllabus has some lateness penalty written up about what if you turn a project in late. I teach a lot of courses and I don't remember what the penalty is, but whatever it says in my syllabus, that's what we're going to do. Certainly getting it in as soon as possible will minimize that penalty, okay? All right. Okay, let's jump in here. So I'm assuming we did okay here to determine if 4 - 1 satisfies one equation or a second equation or the system, the two of them together. And then we do this graph, and I'm not going to pay any attention to the actual lines themselves, but I'm just going to draw like 2 random lines. If those are the lines that correspond to the equations, where do you see the solution in that graph? Yeah, so this point right here, what is it? 4 -1. Yeah, all right, so the packet here will not have a lot of meaning unless you heard what we just said there. So that's your solution, right? It's the intersection point. It's the only point that's on both equations, that's on both graphs, which means it's the only point that satisfies both equations. Okay, so there's the graphical way to solve a system of two equations in two letters, two unknowns. But then we've got algebraic ways, which are in a very real sense better, but the graphical way is a nice thing to keep in the back of your mind. Okay, so here we go on the teaching demo. I mentioned this before. The examples we worked with so far, mostly last class, have been solved using one linear equation in one variable. We will expand our ability to solve problems by reviewing how to create and solve systems of linear equations in two variables, or more simply stated, linear systems. Okay, number one, the graph below represents this system of linear equations. One equation is x plus 2y equals 142. That's the one that's in red up on the board, but it all looks like it's in the same color on your page. Go ahead and flip to the next page. The other equation is this -3x plus 10y equals 160 in blue up on the board. All right? So here's what it says. It says that the second equation models the percentage of never married U.S. adults. Percentage of never married U.S. adults, and the other equation models the percentage of U.S. married adults. There's a lot going on in the graphs, and I always need to pause the first time I see a graph like this with some interpretation going on. The horizontal axis, years after 1970. Okay, so ballpark, where are we? Like right now today? 30? Yeah, I think would we be in the 30, 36? 46, right? Yeah, okay, so 46. So this is where we are right there. So we can go up, and we've got one point that's on the blue thing, whatever that means, and then we've got another point that's on the red thing. Just pretend those two lines are right on top of each other. And so what does it mean? So if we take this point and we go over here, I see 30 what? 30%. 30% of American adults, and then that blue line was the never married category. So today, if this bottom graph, the blue graph, is accurate, then what we were saying is that today, if you look at all the adults here in the US, 30% of them have never been married. And if we look at the blue graph in its entirety, that was just a single point on the blue graph, but now we can look at the blue graph in its entirety. It is a line that is sloped slightly uphill. What does that mean is happening over time? Yeah, fewer and fewer, yeah, a greater and greater percentage is never married, right? Greater and greater percentage of adults are never married. Fine. Then we do the same thing with the other graph. So I take my orangey point here and I go over here. That's 50, what? 50% of people today are married. 50% of adults here in the US today are married. And then we look at that line, which is angled slightly downhill. So what's happening over time? Yeah, fewer and fewer, a smaller and smaller percentage of adults are married. Okay, it makes sense that if one of them is going up and the other one's going down, that seems perfectly reasonable, right? Two different sides of the same coin. Just real quick, what was our guess for the green percentage? It's about 30 and the red? 50? What's the problem? Yeah, we got 20% missing, and we got to think about where they are, right? 100% of the pie has to be here someplace. So it seems like we've captured everybody. Either you are married or you've never been married, but there are the divorcees who were married and aren't, and they don't fit in either of those categories. And right now we're saying that that's 20%. Good? Okay. So, like I do all that, we could have just jumped into finding, I think we're going to be finding the intersection point. That's what this lesson is about. But I gotta pause, and I can't think about these trends without thinking about individual points. Once I understand an individual point, I can think about, oh, what's the trend? Uphill, downhill, and I can start thinking about things. All right. Okay, so then it says estimate the coordinates of the common solution, which is also called the intersection point, for this system of linear equations. So go ahead and put a dot right there at the intersection point and fill in the blanks here with the coordinates. Okay, somebody, what do you have? 69 and 38. Did everybody get exactly those two numbers? 6937. Anybody say 70? It's close to 70. It's probably a little less than 70. What does it mean, like in terms of like me grading your work on this? It means there's more than one right answer. Anything you do reading a graph is estimation. So of course there's a range of answers. Okay, so what does the intersection point tell us? Let's see. The 69 is the input. That's the years after 1970. What is that? 2039? I'm doing that right? So in 2039, that's the 69 part. This 38, what is it? 38% of adults. Yeah, we got to say two things here. By virtue of that purple point being on the blue graph, 38% of the population will have never been married, but also 38% of the population will at that moment be married. And that's the spot where it's equal, right? You said equally. Okay, so in 2039, the model predicts, I'll talk about that phrase in just a second. Model predicts that 38% of adults will be married and 38% never married. Okay, and I mentioned I was going to talk about this phrase right here. The model predicts. That is a key phrase. If you don't have that phrase or some variation of that phrase, you can't get full credit for the sentence because nobody knows what's going to happen in 2039, right? This is a prediction here. So assuming that those two lines stay perfectly accurate, then we can say, yeah, 38% married, 38% not, but who knows what's going to happen, you know, between now and then. And so you got to make sure that you convey in your sentence, there's uncertainty here. We're using a model and models are not perfect. It's not a good thing, it's not a bad thing, it's just something to point out. Questions on?
So that the model indicates or
suggests. The model indicates, the model suggests. Yep, all good. Lots of different ways to say it, but just make sure that you are not suggesting that we know with certainty this is what's going to happen. Okay. All right. So the solution to the system of linear equations above was found visually by graphing. That's the estimating this intersection point. However, we can only approximate the solution or intersection point when we use the graph. Next, we'll review two algebraic methods. We mentioned these earlier today, substitution, as well as addition, which might also be called elimination, depending on your past experience. That allows us to find the exact solutions for a system of linear equations in two variables. So exact solutions, whereas some of us said 38 and some of us said 37, but we're not exact yet, right? So here are two methods that we can use to solve exactly. All right, here we go. We're going to solve this system of equations up here twice. Same system, same answer, two different techniques. First one is substitution. Substitution, step one is to solve one equation for one variable. Solve one equation for one variable. So you got four choices here. You could solve the first equation for x, you could solve the first equation for y. You could solve the second equation for x, you could solve the second equation for y. Sometimes all four of the choices are roughly equally easy or equally hard. But if there's one of the options that's easier than the others, then you're going to make your life fraction free if you pick that option. So let me show you a bad choice, and you can write it if you want to. I say bad, there's nothing wrong with what we're about to do, it's just going to involve fractions. And if we can avoid it, I would. Suppose that we solve the second equation for y, just picking one. Second equation for y. So first thing I need to do is move, I've got two things that need to move, the negative 3x and the 10. Both have to make their way to the right-hand side. Which one has to go first? The negative 3x. And we're going to add that to both sides. So that makes it 10y equals 160 plus 3x. Agree? And then we move the 10 by doing what to both sides? Then we'll divide both sides. And we get 160 plus 3x over 10. Totally correct. We can get to the right answer with this as a starting point, but it's got fractions. And of those four choices that I said, the x and y in either equation, one of those choices will avoid fractions entirely. Can we see which one? Top one for which letter? For x. Why did we have division? Why did we have this fraction looking at the original equation? Yeah, what? So did you see the 10 in front of the y that ultimately we had to divide by? So if you choose the x in that first equation, there's an invisible 1, there's nothing to divide by. So that's the best choice. So we're going to instead solve the first equation for x. We got to move the 2y over by doing what? Subtract. So we get x equals 142 minus 2y. Done. No division, no fractions. Once you've solved one equation for one variable, you substitute it into the other equation. So here's what we're going to do. We're going to copy that other equation, -3. I'm going to leave a blank space where that x is, plus 10y equals 160. So that's copying the other equation, the second one in this case, leaving a blank where the x was. And what we know from the first step is that x is equal to 142 minus 2y. They are one and the same, which means any place I see an x, I am welcome to put what instead? 142 minus 2y, right? There's no funny business there. We're just trading one thing for something that's equal to it. It's like 5 nickels and a quarter. They're the same. It's just a swap. It's an even swap. Notice the parentheses. Got to have them there. What's the best thing about that equation compared to the original two that we started with? What makes this one better? There's no fractions. That's good. First two equations had no fractions, though. Why is that this new equation better than the first two? It's got only y's. It has only y's. The first equations had x's and y's. So we have made things much simpler. Okay, so we distribute that -3. What is that? -426. Is that right? 426 plus the 6y. Don't forget minus minus is plus. Plus 10y is 160. And then we can start to combine like terms, right? So -426 plus how many y's? 16y is 160. Add that 426 to the right-hand side. 586. And then do what to both sides? Divide by 16. 586 over 16. What is it? This? Okay, anybody else get that? Okay. All right. Are we done with this problem? No, what do we still need? Still need x, right? And we need to have an x and a y, just like up above in the marriage question, we gave the coordinates, two numbers, an x and a y. So you are welcome, now that you know that the y is for sure 36.625, you're welcome to go to any equation on the board that has both letters in it. You just need an equation with both x and y, all right? But it turns out there's one best place to go. Anybody know which? I don't think that's the best place to go. It's not terrible to go there. Yeah, Matt. That's the best place to go. Because what did you just say we needed to find? X. And that equation is perfect for us because it starts x equals. So once we do the arithmetic, we've got x. That's the best place to go. Okay, so 140 x equals 142 minus 2 times, and then what are we putting here? What are we putting here? So I still got my 2 times, so 36.625. Those right there. Yeah. Okay. So what's the final number? That's after the subtraction. Okay. So we've got X, we've got Y, we're done. Typically, you'd write it as an ordered pair, just like we did up above. So 68.75, comma, and then 36.625. Any questions on that? Okay, so there's the method of substitution, so-called, because you are substituting into one of your equations. I kind of made a big stink about, once you have solved one equation for one variable that you plug into the other equation, things go really funny if you inadvertently plug into the original equation. Like if you use the first equation like we did to get this purple x equals, if you accidentally plug that into the first equation, there's nothing wrong with it, but you'll see what happens here. I'm going to erase this in just a second, but x plus 2y, right? Instead of x, what are we putting? This 142 minus 2y, right? So just substituting just like we did before. There's nothing wrong with it. There's x. That's the x plus the 2y equals 142. And what happens with my two y's? They cancel, and so what does that equation become? 142 equals 142, which is true, but not helpful, right? And so that's why you want to use the other equation. So solve in one equation, plus substitute into the other, right? Okay. All right, that's the method of substitution. Instead, we could try the method of elimination. Let's give that a shot. Okay, I'm just going to copy those two equations again down here just so we can kind of start over. Somebody read, Jasmine, can you read the first equation? And the other one? Is that right? 160? Okay. All right, so here's the other method. What we are going to do is add the two equations together. Don't copy this down, but I'm just going to add it right here. Don't copy. When I add up the x's, what do I get? Negative 2x, right? Combining like terms. When I add up the y's, plus 12y, and then I add up the right-hand side, 302, 302. Okay, there's another equation that is absolutely true. I haven't done anything wrong. But remember, the thing that made the previous method work, going back to this equation right here, what did we say made this equation better? It's only y's, right? Only a single letter. So have I made any progress by writing this new equation? No, it still has two letters. It's still valid, but it's not any better. And so adding the equations is something we're allowed to do, but we want to do something else before we add them together. So I'm going to do something that will look funny if you don't know where we're headed here. If you do, then it won't look funny at all, but I'll explain why we're going to do what we do in just a second. I'm going to take this first equation and multiply both sides by -5. -5. Again, if it's mysterious, don't sweat it. We will explain. -5 times this side and -5 times this side. Again, even if you're not sure why, it's legal. Yes? Did the same thing to both sides. Okay, so let's write down below what we get. Get rid of this here. Okay, why there? All right, what do we get? Distributing on the left, -5x, and then minus 10y equals, I don't know, -710? Somebody help me out there. Is that right? Hey, I'm here all week. Thank you. All right, so let's take a look at these two equations, the bottom two, ignoring the one that we started with. We're welcome to add them up just like we did before, right? But something better is going to happen when we add these equations. When we add the x's, what do we get? -8, adding those x's, right? When we add the y's, what do we get? cancel. Aha. When we add the right-hand sides, I don't know, 550? Somebody check me. Am I right? Yeah, negative 550. Okay. Is this equation any better than the ones that we started with? Yes, it only has one variable and not two. Solving the rest of this problem is going to be pretty straightforward. So we got to just make sure we're clear on that mystery, that negative 5. Why? Yeah, I picked negative 5 looking for something that would give me an opportunity to cancel the y's. And so before we had that negative 5 there, I said, oh, I currently have 2y and I currently have 10y, and I can make the top one, not just 10y, but what did I make the top one? I made the top one negative 10y, and then I add them and they just disappear. Pete. So let's suppose we multiply the top equation by 3. What do you get for the x's here? 3x. Is that a good thing or a bad thing when we add? That's a great thing. So multiplying the top equation by 3 is the other natural choice. No better or worse. In fact, it's probably a little bit easier than what I did. I wanted to multiply by a negative, so I picked that one. Okay, so let's finish. To solve this for x, we got to divide both sides by negative 8. So we get x equals negative 550 divided by negative 8. Because I'm so freaking smart, I'm going to do this in my head. 36.62. Oh, that's why. Oh no, hold on. I'm still smart. What is it? 68.75. 68.7. You guys see right through me. All right, so that's x, right? We just do the division. What do we still need? Still need y. Remember how I said there was one place to go on the previous problem? There was a best place, like we knew the value of y, and then we went to the x equals equation. This is one downside to the method we're about to use. There is no simple place to go to find y. We're going to have to do a little bit more algebra to find y. So I would pick either of the original equations. How about we pick this second one, the negative 3x plus 10y. So here it goes. This equation, negative 3 times, I'm going to put just some blank space there, plus the 10y equals 160. Everybody see what we have there? Just copied that equation. And instead of the blank space for the x, what are we putting? 68.75. Okay, so it's still like a substitution happening, even though this isn't the substitution method. Still need to substitute to find the second variable. Okay, I think that's good. All right, and so that equation, we just have some work to do to find it. It's not hard work, but we got some work. All right, so 3 times this. Somebody help me, what is that? 206.25 plus the 10y equals 160. And then solving for y, so we'll add the 206. So we get 10y equals, 366.25. And then we divide by the 10, 36.625. So that's our answer. Again, probably want to write it like we did in blue here with the coordinates, 68.75 comma 36. Any questions on the addition method? Why is it called the addition method? We added equations, right? But usually you got to do a little bit of work before you add the equations together. Got to do work to get some of these variables to cancel. In this case, we just had to multiply the one equation by negative 5 or the one equation by 3. But there are other equations where you'd actually have to multiply both by something. So just be prepared. It's not always as easy as just multiply one equation by something. You might have to do work to get both variables to match up, all right? Okay, so on the next page is this investment problem. Lots of words, a box to kind of get our answers all organized and stuff. But the fact is, I just kind of feel like I've already talked long enough today, and so I'm just going to skip that one. And you're going to start this activity here. So you're going to do some reading here. This talks to you about break-even analysis In italics is a problem about wheelchairs that you are going to solve on the next page, okay? So the problem is written out in italics here. You don't need to write anything on this page. The next page will guide you through the process to start writing variables and definitions and equations, okay? Raise a flag if I can help.